Hello students, so in this video we are essentially trying to show some properties of eigenvalues and eigenfunctions, right? See, the thing is for this particular problem we are only going to concentrate on the regular Sturm Liouville boundary value problem. So basically consider a regular Sturm Liouville boundary value problem. Okay, and we have that, right? You guys already know. So essentially we can just write it like L of y plus qx plus lambda sx times y is equals to 0. This is between x in a and b, and y at the point a equals to sorry, this is periodic, right? I'm sorry about it. So essentially a1 times alpha, I wrote it like alpha, right? Alpha 1 times y at the point a plus alpha 2 times y prime at the point a is going to be, let's say, 0, and alpha 1, and beta 1 y at the point b plus beta 2 y prime at the point b is equals to 0. Yeah, so you remember this is the condition: alpha 1 square plus alpha 2 square not equals to 0, and beta 1 square plus beta 2 square not equals to 0. Okay, what are these two conditions gives you? These conditions actually make sure that, so basically these two condition make sure that we are dealing with a boundary value problem, right? So boundary value problem, yes. And these two conditions, this one and this one, these are the regular Sturm Liouville boundary value condition, and of course you have the equation which we are writing it as 1. Now we were talking about eigenvalues, right? So essentially the question now was to find lambdas which admits non-trivial y. Okay, find lambda in C which such that there exists y not non-trivial solving 1, right? Solving 1. Okay, so with that aim, what we needed to is, we saw that if you have a regular Sturm Liouville problem, then you always have the eigenvalues are real, right? So basically these we can think of it as R only, so it's not C. Yes. Now the question, the most important question is this: see, this is a general problem, right? Now what is the guarantee that there are eigenvalues? There will be an eigenvalue. So let's say given a lambda, fix a lambda for any such problem, given a lambda. So you see, this L can be a general operator, right? Q can be any function, and S can be any nice smooth function. So what is the guarantee that there is existence of eigenvalue, right? So there is a guarantee, and the thing is, the proof is very complicated. We are not going to go there. I will state the theorem, but we'll try to understand it using an example. So let's look at an example. So we want to talk about this thing problem: y double prime plus lambda y equals to 0. Yeah, this is the problem, and we are considering it x is between 0 and 1. Okay, and of course another thing is y0 equals to 0, and we are considering this problem. So a little complicated than whatever we did up till now. Yes, so y at the point 1 plus y prime at the point 1, let's say that is going to be 0. Yeah, this is just some problem which we are considering. So basically here, if you think about it, alpha 1 is 1, so here alpha 1 is 1, alpha 2 is 0, beta 1 is 1, and beta 2 is 1. I hope this is clear. So this is some regular Sturm Liouville boundary value problem, no issues. Now what is the general solution? We, without thinking about it, we can just write it down. The general solution is given by y of x is a cosine root lambda x plus b sine root lambda x. Yeah, I'm not solving it, but it is very easy to do, right? You remember that e power mx type of thing you can do, and you can just find out the general solution. Now let's put the initial condition. See, since y0 equals to 0, yes, if you put y0 equals to 0, so basically this is the only thing it is remaining. So and this is gone, right? So basically it means that a has to be equals to, so this is a equals to 0. So basically we are only left out with b sine root lambda x. So y of x is b sine root lambda x. Yes, again, why is it true? Y at the point 0 is what? A times cosine root lambda 0. Yeah, cosine root lambda times 0. So this is going to be cosine 0, which is 1. Yes, plus b sine root lambda times 0. This is going to be 0. So basically you are only left out with 0 equals to a. Okay, so a is going to be 0. So essentially the first term is gone and we are only left out with this. That's the idea. Clear? Now let's just understand the next one. Now we have the next condition. Again, see, y at the point 1, yeah, is what? Let's just understand y at the point 1. So now you see, the thing is we do not have to put the value of, this condition we want to employ. We do not have to employ it on this equation. Yeah. Why? Because we already have y reduced to this particular part, right? That yx is b sine root lambda x. This we know. Okay. So if we put it, you see, it gives b sine root lambda x is 1 in our case, plus see y prime of y1 is there, right? Y prime of 1, and y prime of 1 in our case is, if you take the derivative, you see y is b sine root lambda x, right? So y prime equals to b root lambda cosine root lambda x. Yes, so if we put it here, it will give me b root lambda and again cosine root lambda, and x is 1, so that is going to be 0. Clear? Okay. Now you see, what do we already have? We already have that a is 0 from this condition. Yeah. Now in this equation, you can take b common here, so you can write it like this: b times sine root lambda plus root lambda cosine root lambda. Yeah, this is going to be 0. But the thing is, here you see we can put either b is 0 or this particular term is 0. Yeah. But if b is 0, then a and b are both 0, and that is not going to give us the eigenvalue. So hence this actually says that sine of root lambda plus root lambda cosine root lambda is equals to 0, and b is of course non-zero. Yes, because we are looking for a non-trivial solution. Now you see, we can rewrite this thing. We can rewrite it, and we can rewrite it like this: tan of root lambda, yes, equals to minus h times root lambda. Here, okay, and of course you can put it as a parameter. Let's say this is some alpha, so that will actually give us that tan of alpha equals to minus h, sorry, not h, one second, minus root lambda. Okay, so that will give me that tan of alpha equals to minus alpha. Yes, see, now this is the equation. So here alpha is root lambda. I need to find lambdas. How many lambdas are there? See, this is the equation which I got. Now the thing is this: can we solve this equation? Of course, you do realize that solving this equation is very difficult explicitly. Okay, so explicitly solving is very difficult. I am not quite sure whether it is possible also. Explicitly solving very difficult, right? Is difficult. So what we do is this, but the thing is we need to know that if there are lambdas which satisfies this equation. Okay. Now, if you look at the graph of this thing, see, I will just give you a small idea of the graph of this. Yeah. See, I mean, the tan, this thing, the graph of the tan. So this will look like this, right? I mean, the drawing is not very good, but you have to excuse me for that. It looks something like this. Yes, I'm just doing one thing, and since this is periodic, it will just okay. So essentially, this is 3 pi by 2, okay, and then the other part is pi by 2, okay, other part is pi by 2. So here, oh sorry, I should put it this way. Okay, this is pi by 2. Okay, pi by 2. Okay, and this is of course the pi line. So you see, if you can consider it, you can find alpha 1. You see, you can find alpha 1 where this actually intersects. Okay, so what I meant by this is, I mean, by looking at the graph you can see that this is happening. Okay, so what I meant is to, I mean, but just by, I mean, you understand this is periodic, right? So this will go on and on. So for every part of this, you will have a root of this equation. Yes. Okay. Even if you are not convinced about it, see what you can do is this. You write it like this. Let's say h of x is tan x minus x, right? That was the possible tan x plus x, tan x plus x. Okay. And here you fix x between pi by 2 x and 3 pi by 2. Okay, and you check that there is a root of this equation. So basically there is a 0 of this equation. It is not very difficult to check, right? As it tends to pi by 2, as it tends to 3 pi by 2. Okay, there is a root of this equation. So hence there is one root, at least one root in this between pi by 2 and 3 pi by 2. And of course, since this is periodic, it will go on doing this thing, right? I mean, it will, I mean, infinitely, there are like infinite number of such things happening. So we can say that to each root alpha n, okay, there corresponds a eigenvalue. There exists an eigenvalue. What is eigenvalue? Lambda n is, you remember, it is alpha is root lambda. So lambda n is alpha n square. Okay, this is for n equals to 1, 2, 3, it goes on. Okay, so what we have is, we have a ordered sequence. So this is very important, ordered sequence, okay, of eigenvalues. And how does it look like? It looks like this: lambda 1 less than lambda 2 less than lambda 3 in this case. Yes, in this case. Okay, and you see, if you notice, you see these lambda n's. Okay, if you notice, actually you see this alpha 1, alpha 2, the roots which you are going to get, as n tends to infinity, you can say that limit n tends to infinity, lambda n's is equals to infinity. So basically the limit goes to infinity. I hope this is clear. And what is the corresponding eigenfunction? The corresponding eigenfunction in this case, eigenfunction is given by r sine of root lambda n x. I hope this is clear. Okay, again let me emphasize what's happening. This is the equation. Yes, I need to find out if there are lambdas which solve this equation. How do you do it? It can't be explicitly done. So what we do is, essentially we fix this interval pi by 2 and 3 pi by 2. Yes, and in this interval you can see that there is a root of this equation. Yeah, so show that there is a root. This is a question for you. Show there exists a 0 of h in pi by 2 and 3 pi by 2. I hope this is not very difficult for you to show, right? This is just an intermediate value theorem. This is a continuous function, right? So intermediate value theorem, yes. So you just show that this is going to be 0 somewhere. Once that is true, you can actually show that in this interval there is 1 0. So, and the thing is, this is like a periodic function, right? This tan. So essentially it will go on doing the exact same thing. So basically you will have a alpha 1, you will have a alpha 2 somewhere here, and you will get a alpha n somewhere here, and you understand that as n tends to infinity, these alpha n's will go to infinity. Okay, so that's the idea. So this is an example of showing that there are, I mean, generally lambdas. Of course, it does not show that general problem has, eigenvalues, but it's just a, how do I put it, way of looking at it, that there are eigenvalues and such that the eigenvalues behaves like this. Yes, and the thing is this, there is this theorem. This is very, very important theorem. Okay, the proof of this thing is not included. If you want the proof, you can go to the book Coddington ODE book. Okay, ODE. Yeah, the book is not for beginners. Okay, this is a complicated book, but if you want, you can look at this book. You can get the proof of it. So, what is the theorem? It says that a self-adjoint operator. You remember we talked about a self-adjoint operator. A self-adjoint operator. So, in this case, it's a regular Sturm-Liouville boundary value problem. So, it's a self-adjoint operator. Self-adjoint regular Sturm-Liouville system. Okay, has, and maybe I can write the theorem in this part. Okay, let me put it this way: has an infinite sequence of real values Okay, what are the real values? Lambda 1 less than lambda 2 less than lambda 3 less than, and it goes on like this. So, basically it starts from on lambda 1. Yes, so there is a number where it starts. Yeah, this is a real number essentially. You remember all the eigenvalues, if they exist, they are going to be real. So, here it is saying they are exist. So, basically this is a real number. So, you can have a ordering of that. So, what it is saying is it starts from some lambda 1. It can be 5, it can be minus 10, whatever, it starts from somewhere, right? And then what happens is there is this strict inequality, see, greater than, strictly greater than. So, there is a second eigenvalue which is greater than first one, and it goes on like this. Okay, yes, with, very important, what happens if there is a bound on this thing? No, it says that limit n tends to infinity, lambda n is going to infinity. I hope this is clear. Okay, and we can also say that for each n in n, okay, the corresponding eigenfunctions phi n, the corresponding eigenfunctions phi n, functions phi n of x, okay, is uniquely determined. You remember, right? It becomes a constant times each other, right? So, uniquely determined up to a constant factor. Okay, this we already had some idea, right? We proved it. See, the thing is this, another thing very important. Let us talk about this thing, that can we say something more about this eigen functions phi n? Yes, we can actually. What we can say is this: it has exactly, yes, n zeros in the interval, a b. Clear? So, you do realize what I am trying to say here. See, what this basically says, that if you have something like first eigenvalue lambda 1, the corresponding there will be a lambda n, right? There will be a lambda n, let me put it this way. Let us say there is a first eigenvalue lambda 1, there is a corresponding eigenfunction which is phi 1 of x, right? Now, you see this phi 1 of x, the question is this: does it have any zeros? Okay, so this says that this has exactly n zeros. So, phi 1 has 1 0, phi 2 will have 2 zeros, and it goes on doing that. Okay, so this is a existence theorem. The proof again is very complicated. We are not going to this proof. If you want, you can find it in Corrington. And the thing is, but this actually guarantees that there exists a infinite sequence doing something like this. Okay, right. Now, the question which we really need to ask ourselves is, are these also valid? So, the question, yes, the question is this question: are these properties valid for a periodic Sturm-Liouville boundary value problem, Sturm-Liouville boundary value system, or problem, whatever you want to call it, problem. Okay, so basically what happens is, you have this equation, right? Ly plus you remember we are talking about this equation, right? Ly plus Sx plus lambda times Rx y equals to 0. That's the equation, yes. And the boundary condition, you have a periodic boundary condition. We are not talking about the regular Sturm-Liouville boundary value problem. So basically you have y at the point A equals to y at the point B, and y prime at the point A equals to y prime at the point B. Okay, and there is an extra assumption also. This assumption is there. See, there is a p of x which is included in L, right? If you remember what is L. So also see here L of y is nothing but p, let me put it this way. L is this operator, right? This is d dx of p d dx plus q. That's your L, right? So what happens here is this. See, this p and q, these are smooth functions. But the thing is, for periodic Sturm-Liouville boundary value problem, you have the same equation. Equation does not change. Just the boundary conditions change. So what happens? Ya becomes yb, y prime a becomes y prime b. So they are same essentially. And p of a is assumed to be equals to p of b. So if something like this happens, then you have a regular Sturm-Liouville, periodic Sturm-Liouville boundary value problem. There is a slight difference in this thing, yes. Okay. So for example, let's say if I give you this y double prime plus lambda y equals to 0. Okay. See, here p is 1, here p is equivalent to 1. So p of a has to be equals to p of b. So let's say this is in 0, 1. Okay. And the boundary condition is y at the point 0 is y at the point 1, and y prime at the point 0 is y prime at the point 1. Okay. So you see here p is 1, so p of a will be equals to p of b, and again these two boundary conditions is easily satisfied, as you can see. So this is a example of a periodic Sturm-Liouville boundary value problem or system, yes. Okay. So now the thing is this, now the question is this: can we say similar sort of we talked about this thing, the properties of eigenvalues. So if you remember, we talked about this thing. See, that the eigenvalues of a regular Sturm-Liouville problem is unique except a constant factor. So basically, if there are two eigen functions phi1 and phi2, then phi1 has to be c times phi2, right? Those things are there. And then the eigenvalues has to be real. If you remember, we talked about this also. And then we talked about the property that this property that if they has to be orthogonal to each other, right? Phi1 and phi2 are orthogonal to each other with respect to the weight function s. Okay. So the thing is this: can we have similar sort of things for a periodic Sturm-Liouville problem? So theorem 1 about the orthogonality. Yeah. So this is actually true. You can actually show. Go through this proof of this. This is a question for you. Go through the proof of this particular thing. Okay. This proof of theorem 1. Whatever we did. This is in the earlier lectures. So go through the proof. Use this condition here. See, here boundary condition is utilized here. Okay. So you have to change this part to your periodic boundary condition, and you show that this is also true. This property is true. Again, the next property. What is the next property? The next property is the all eigenvalues of a periodic Sturm-Liouville boundary value problem. Are they real or not? Yes, they are real. Okay, you can show that also. Exactly the similar sort of thing. You just have to change the boundary condition here. Here, you just figure out how to put down the boundary condition. Okay, right. See, if you look at this thing, even this self-adjointness, the Sturm-Liouville operator is self-adjoint. This is what we used to show this real thing, right? So you can actually show that the Sturm-Liouville operator given with that periodic boundary condition is also going to be self-adjoint. Here the boundary condition is regular. There you have to replace it with periodic, and similar thing holds. Okay. Now this will be, now you can ask that what is the point, everything is same. No, it's not. See, this particular theorem, theorem 6. Okay. So basically the other two theorem that holds, but theorem 6 does not hold. Okay. So what I will do is, maybe we will put it in an assignment. So we will show that theorem 6 does not hold for periodic Sturm Liouville boundary value problem. Okay, this is a big thing. You have to note that this does not work for periodic Sturm Liouville boundary value problem. Okay, right. So the thing is this. So with this, and what about the existence? Existence also similar sort of thing works. Okay, I will give you an example assignment problem where you will see exactly how different it can be. It is a little different. How different it can be, and then as a part of assignment I will give you this theorem. So basically you can compare it with periodic Sturm Liouville boundary value problem and regular Sturm Liouville boundary value problem. So I hope you understood. For regular Sturm Liouville boundary value problem, you have all these theorems. Yeah, the eigenvalues are real, orthogonality is there between eigenfunctions, and so basically one will be a constant times another, that property is there, and this existence theorem is there. So all of this is not true for periodic Sturm Liouville boundary value problem. Most importantly, theorem 6 does not hold for periodic boundary value problem. Okay, with an assignment I will give you this one, and I will also put this theorem down. So the problem will be set up in such a way that you can actually compare that with your theorem and see what's happening. But exactly same is something similar happens, that you can actually show that there is a lambda which like an infinite sequence, and lambda also goes to infinity. So those things are there. Okay, so with this we are going to end this video. Thank you.